Digital Industry Software Tessent Embedded Analytic A Summary Guide. Executive Summary Tessent Embedded Analytic provides semiconductor intellectual property (SIP) that allows designers to incorporate intelligent self-analytic capabilities in systems on chip (SoCs). Embedded analytic technology helps solve the most pressing problems faced by the high-tech industries today, including cybersecurity, functional safety, and management of the complexity. It also allows the designers to develop SoCs more quickly and cost-effectively. Embedded Analytics offers a suite of the semiconductor IP that allows chip designers to integrate an intelligent analytical infrastructure into the core hardware of their devices. By monitoring and analyzing the real-world behavior of the entire systems, engineers can take action to reduce the system power consumption, increase performance, protect against malicious intrusions, and ensure the product safety. These capabilities address the applications in a broad range of market sectors, from automotive and IoT products to scale computing and communications infrastructures. This document provides a summary of the Tessent embedded analytic IP component and is intended for engineers, managers, and associate development teams who want to evaluate a Tessent portfolio of IP. Contents. Okay. So, embedded analytic product overview. The embedded product analysis portfolio includes more than a 20 modules that the SoC system architect can use to monitor and analyze the behavior of any mixture of licensed IP and custom logic designed in-house. The system architect and the design team have complete the freedom to choose which blocks to monitor and to what level of the detail. Embedded analytics includes its own on-chip message-based communication architecture that makes the entire host interface agnostic. Modules range from dedicated optimized IP to highly parameterized modules that are configurable at design time and runtime and fall into four broad categories. Analytic modules. Analytic modules are smart modules that gather and pre-process data from various function blocks on the chip. They are configurable at runtime, including comparable to comparators and counters, and in many cases, transaction aware, allowing the designer to focus in a specific area of interest in the SOC behavior. The secure message infrastructure. The secure message infrastructure is a flexible and scalable message fabric that integrates or embedded analytic IP and supports configuration, data collection, and cross-triggering. The message fabric is built from the universal blocks that can be connected hierarchically and allowing the prioritization and routing of the messages and real-time events between their interfaces and providing security features such as locking interfaces and authentication transport. Communicators. They allow the embedded analytic IP to interact with the software running on a main system or an external debugger. Embedded analytic has a range of external communicators, starting with the traditional debug over JTAG, extended to a higher speed via USB 2 and super speeds using the EBC for USB 3. Additional communicators enable connection to PCIe over the AXA bus and an URL upload over the high bandwidth address links. Analytic modules. Bus monitor. The bus monitor provides complete and transactional level visibility of SOC activity across all major bus standards, including AXI, ACE, and OCP. The bus monitor analytic module provides a wide variety of the monitoring functions. It can be used for analytics, reporting diagnostics, and performance profiling and other applications. The Modbus monitor is transaction aware. It can monitor each individual transaction everywhere there where even where there are multiple outstanding simultaneous transactions underway, which may complete out of order. So Tessent embedded analytics bus monitor has visibility across the SoC and since it monitors transactions between the on-chip blocks on the SoC bus. It allows the analysis not just of the behavior of the individual blocks, but of the complex interaction between those blocks and the software running on them. Each transaction aware, analyzing and interpreting data locally in hardware with filters and counters, allowing it to turn raw data into useful information, increasing each value and decreasing the transfer bandwidth and reducing the time needed to process and understand. Can construction complex trigger scenarios based on activity, capture bus activities up to and after a programmed trigger event into a circular bus trace buffer, allowing visibility of what led to a trigger event occurring. The DMA, Direct Memory Access. Direct Memory Access, DMA. The DMA analytic module provides direct memory access to a system memory from the debug host. It enables an external application to issue transactions on the bus fabric in order to read or write a block of memory. This module enables program loading in a Tessent embedded analytics system as well as directed memory inspection via read accesses and manipulation via write accesses. Tessent embedded analytic DMA provide a connection from a Tessent embedded analytic infrastructure to anywhere in system memory, equipping the designer with a highly efficient mechanism to transfer external data in or out of the memory and meaning that a conformer or a boot code can load it in onto the CPU. Without using slow JTAG connections, speeding the up to the SoC high bring up the process. Each instance of the DMA modules can include up to 16 independent DMA channels, allowing up to 16 DMA transfer in occur in parallel. The module supports two modules of the DMA operation immediate for transferring a small amount of the data up to 16 bytes and a normal for a large DMA transfer up to 64 kilobytes. Can be configured such that a received real-time event trigger a DMA transaction or a real-time event is generated on the completion of a DMA operation, which means that the Tessent embedded analytic infrastructure can integrate seamless and flexibility into SOC operation. The Embedded Enhanced Trace Encoder ETE, the Tessent Embedded Trace Enhanced Trace Encoder is a free-featured RISC-V trace solution that provides a mechanism to monitor the program execution of a CPU in real time. It encodes the program execution instruction trace and optionally the data from load and store instruction data trace, outputting the trace in a highly compressed format. External software can take this data and use it to reduce construction, the program execution flow. The trace encoder can be finely tuned to balance the features and get count requirement of your system. The trace encoder includes a broad range of filters and giving a complete control over what and when to trace. Examples including filters to enable tracing within an addressed range at a specified privilege level of instruction service routines for a fixed period of time, starting and stopping on external events, and that the trace The Tessent embedded analytics enhanced trace encoder. The enhanced trace encoder complies with the latest standard produced by the RISC-V International Efficient Trace for RISC-V Trace Working Group. It supports any standards compliant RISC-V processors, can trace the execution of the multiple concurrent instructions from the multi-issue CPUs and a speculative or out-of-order instruction execution. Support all RISC-V option trace modules, including the implicit exception, subsequently infallible jump and explicit return and branch prediction and jump target cache and full address. The optional variant supports cycle-accurate trace, which provide timing information that allows users to determine when each instruction retires. A non-intrusive fast profiling mode only reports to the address of the instruction immediately following an exception, call or return, ideal for code profiling. Timestamp provides basic profiling support. So, the GPIO trigger modules. The GPIO trigger modes can be used to connect the Tessent embedded analytics infrastructure to other parts of the system in order to provide event and configuration functions such as event inputs, outputs, and GPIO. Each input event if interface can be used to initiate a real-time event and/or embedded analytics messages on the downstream message interface. Alternatively, these events can be converted into I/O signals that can be wired to physical I/O pins to enable interaction with external tools such as oscilloscopes. An output event interface can be used to generate signals, either post or with the handshake acknowledged, when real-time events are received on the upstream message interface. Additionally, input event values can be passed through to the output event pins. So the input and output event signals are suitable for the connection to the control and status signals of a process core to allow cross-triggering integrated of a Tessent system with that core. The Tessent embedded analytics GPIO provide a mechanism for controlling hardware signals from a Tessent embedded analytic domain for sample SOC level signals into the embedded analytics domain. It facilitates two-way communication between the SOC and embedded analytic domains. Can be used to configure and control other functions within the device such as clock controllers, soft reset logic, power controllers, debug modes, and system modes, or to force internal signals via glue logic whilst debugging. Can be mapped to the proprietary trigger systems such as the ARM cross trigger interface in order to integrate such systems with the Tessent embedded analytics, further expanding the architecture and agnostic functionality of a Tessent on-chip analytic subsystems. The network on-chip NOC monitor. The NOC monitor provides complete and transaction-level visibility of SoC bus activities for devices using the ARM 5 Coherent Bus Interface CHI. The NOC monitor can be used for analytics, reporting, diagnostics, and performance profiling, and support the need for fast and non-blocking data transfer between the multiple fully coherent processors within an SoC. The Tessent embedded analytics NOC monitor has visibility across the SoC system since it monitors transactions between the fully coherent blocks on the ARM, the ARMBA 5 CHI. It allows analysis not just of the behavior of the individual blocks, but of the complex interaction between those blocks and a software running on them. Is transaction aware, analyzing and interpreting data locally in a hardware with filters and counters, allowing it to load data into useful information, increasing the value, decreasing the transfer, balance, and reducing the time needed to the process and understand. Can construction complete trigger analysis based on the bus activities? captures bus activity up to and after the programmed trigger event into a circular bus and trace buffer, allowing a visibility of while ready to a trigger event occurring. The processor analytic modules. Processor analytic modules couple processors or their processor-specific debug port to the Tessent embedded analytics systems. They are intended to control the process core, extract processor-related state information and performance data, as well as integrated with the processor existing debug support, which may additionally provide instruction and data sorry, under the data trace. A process analytic module PAM enables features including already PAM, the run control, run, step, halt, and access to the breakpoint and watch point resources. Figure 6 is this process analytic module connectivity. So these resources and performance monitoring unit for cache hits and etc. Cross-triggering and event-driven control, event generation and periodic sampling, PCN connected and etc. Integration with the processor-specific debug support. There are two main variants, the BPAM, Bus Processor Analytic Modules, and the JPAM, JTAG Processor Analytic Modules. The BPAM interfaces to the processor using a bus control and the JPAM using the JTAG protocol. And the processor analytic module for processors with the bus debug interface BPAM. The BPAM can be used with the debug interfaces following the AXI and APB bus standard, including core from the RAM. Processor cores from the ARM have a variety of interfaces to enable connectivity with this core site debug technology, which can also be used to connect the Tessent embedded analytic systems and either directly or via existing core site infrastructure. Figure 7, direct and indirect coupling of the BPAM for ARM cores. BPAM is a cores infrastructure. And the processor analytic module for processors with the JTAG debug interface, JPAM. JTAG IEEE 1149.1 controlled cores can be accessed using the JTAG processor analytic modules, JPAM, as shown in Figure 7. Many fiber processors, for example, use JTAG as a debug transport. The JPAM provides a bridge between the Tessent embedded analytics system and a JTAG interface, allowing full control of the tab state machines and its associated instruction and data registers. It's been designed to provide access mechanism to process the code which implementation a JTAG debug interface. However, it is suitable for interfacing to any component or subsystem which implement the IEEE 1149.1 standard JTAG. The JPAM is available in two variants with and without a JTAG signal pass-through capability. This capability allowed the target JTAG interface to be controlled directly from the chip pin when the JPAM module is disabled. The processor analytic modules connect a processor debug port into a Tessent embedded analytic systems, providing the essential visibility of CPU activities and the status to enable the analysis and the debug of the SoC. Enables the long control of the target processor and access to the breakpoints and watch point, facilitating the functional interaction with the core needed to enable analysis and debug. Offers low latency, computable close, triggering the close to the rest of the Tessent embedded analytics portfolio presented within the SoC. So, for example, a watch point activated on one PAM and one subsystem of the SoC can hold a processor in a different subsystem, allowing a holistic approach to analysis across the subsystem. Figure 8. coupling of the JPAM for processors with the JTAG control. Static instrumentation. The Tessent embedded analytics static instrumentation module provides a communication path from an embedded software to the debug host. This is achieved by providing an address to space made up of multiple independent channels, each supporting 32 mailboxes, allowing embedded software to pass data to the debug host as well as causing a real-time event to cross-triggering with other embedded analytic modules. The module enables engineers to instrument their code with a low-level instruction to debug the execution flow, as well as more sophisticated uses such as collecting the software instrumentation trace data from operating system APIs. Figure 9 is static instrumentation connectivity. So, Tessent embedded analytic static instrumentation is a solution based on both hardware and software. Code can be instrumented with just a single instruction, meaning watch points can be inserted in software with a minimal effect on runtime code. Can pass out parameters from a SOC to debugger when a watch point is reached, giving a greater visibility of code activity and health, and allowing the possibility to pass out larger data structures without calling on trace. They provide a communication path for embedded software APIs to pass data to the debug host for analysis and visualization. The status monitor. The status monitor provides visibility and monitoring of any circuitry within the SoC. It offers many of the benefits of a logic analyzer, but with no need to bring signals off chip. The status monitor provides a wide variety of the functions, including the debugging, report diagnostics, and performance profiling. It can be parameterized on and instantiated to precisely monitor the logic signals with the host SoCs that interest the engineering team, giving visibility of those internal signals lines that would otherwise be inaccessible once the SoC is delivered, as well as during the FPGA prototyping or the emulation. So this is the status monitor connectivity, figure 10. And then the Tessent embedded analytics status monitor analyzes on a chip the signals and interfaces. It can measure the performance and verify the design appropriate chip functionality on the chip with total flexibility. Affords logic analyzer type visibility of internal signals not normally detectable off chip. Can be configured at runtime to gather metrics, capture traces data, and interact with other embedded analytics modules to create complex triggering scenarios. The System Memory Buffer SMB. The System Memory Buffer SMB provides buffering functionality for embedded analytics messages by using system memory as temporary storage. When the instantiated bandwidth of the messages containing analytics data is greater than the throughput of the chosen offset communicators, the SMB can store these messages until such a time that a message can be emptied, ensuring that a back pressure does not build in the system, causing precious analytic data be lost. This is referred to a double-ended operation. The SMB's interface is shown in Figure 11 in double-ended operation. So the SMB will autonomously read a message back from a system memory and direct them to the suitable configured communicator, such as a USB to communicator. This is the Figure 11 System Memory Buffer Connectivity SMB. And this single-ended operation is also supported where the SMB only writes the message into system memory but does not read them back. This In this mode of operation, the message must be recovered and processed by another system, such as on-chip processors or directly from a PCIe interface. Once a message has been recovered from a system memory, the SMB's read pointer must be updated, which can be achieved via sending the SMB configuration message or updating the pointer register value from an optional AXI interface. Double-ended operation is shown in Figure 12, where messages from a variety of analytic modules are routed to the assembly before being forwarded onto the trace communicators for off-chip processing. Here, the JTAG communicator is used only to configure the embedded analytic systems. So Tessent embedded analytic system memory buffer provide a two-way communication mechanism between the Tessent embedded analytics the message infrastructure and a system memory. The SMB can perform a variable buffering function in those cases where the analytics subsystem produce a burst of the data faster than a communicators available can add off chip, ensuring that data is not lost. Figure 12 is double-ended operation of the system memory buffer and offer four modes of the operation, including the streaming and traced mode, tracing from a mode and a trace about mode, and the trace mode allow data of the interest to be captured into system memory before, after a round trigger event initiated by Tessent embedded analytics event. The trace receiver. The trace receiver module accepts the trace data typically generated by a CPU and encapsulated into Tessent embedded analytics methods to be transferred off-chip via the message infrastructure, as well as allowing the use of the versatile and high bandwidth interfaces such as USB to extract trace, and this module is also capability of incorporating any vendor's triggering the mechanism into a Tessent embedded analytics-enabled system. This enables powerful cross-triggering across heterogeneous SoCs. The Tessent trace receiver currently supports the following trace protocol: the ARM AMBA for ATB version 1.1, and this is a trace receiver connectivity. The trace Tessent embedded analytics trace receiver can be configured to filter the input stream to accept data from certain trace IDs and discard the rest. It places further downstream in the trace hierarchy and after aggregation of the trace from the multiple sources, which means that it requires off-chip data communication bandwidth is reduced. Can accept the trigger event from the trace interface and choose to emit these as embedded analytics real-time event, or if leave them embedded in the trace data stream or both. Can filter the trace data it captured from an ATB interface based on the characteristics of the corresponding trace bit. Virtual console. The virtual console analytics module provides a preferred interface that enables system software to communicate with an external host via the Tessent embedded analytics infrastructure. The virtual console is intended to replace on a conventional UART-based communication with the system that requires console connections, such as standard I/O for an example, and printf, and those with the operating system and application tasks that can be configured and interacted with the Cedar terminal dialog. It can also be used to correct the software instrumentation in cases where either no hardware filtering is needed or there's a small number of streams. The Tessent embedded analytics virtual console, enables embedded software to communicate with an external debugger This led to the user interacting with the firmware on the target using console-based communications or within the one environment with a single physical connection to the system, giving the user immediate and extensive control over what the target program may do. It is extended to provide a conventional UART compatibility for systems which require console connections. It carries your communication from the chip via Tessent embedded analytics messages infrastructure, removing the need for an additional physical port. Can collect limited software instrumentation, reducing the need for instrument code by other means. So, this is the figure 4 is the virtual console connectivity and the secure messaging infrastructure. The secure messaging infrastructure provided the communication fabric to any Tessent embedded analytics system, interconnecting the analytic modules and communicators, allowing the SoC designers to create a system-wide analysis, optimization, and security implementation. The secure message infrastructure. The SMI is a secure scalable communication fabric which is independent from the main SoC interconnect. It arbitrates and routes messages containing the configuration and analytic data to and from the debug host, as well as relaying the real-time event between the modules for cross-triggering purposes. This is the figure the 15, the secure message infrastructure like this. And this based on the non-blocking architecture. It ensures that real-time events are prioritized and enables crossing triggering between the Tessent modules and reliable data capture and recording. The infrastructure includes security features to disable specific message interfaces in addition to an authentication transport mechanism. The SMI provides the following key functional blocks: secure message engine, message gateway, message lock. So the secure message engine connected the component to the Tessent embedded analytics system together, routing the message the real-time event between the modules over its message interfaces arranged into three topology. Real-time events are those which take precedence over other communication in progress. As, for example, a Tessent module would give them priority over the buffered messages using to be sent. This is the figure 16, the secure message engine connectivity. The message gateway module provides a capability for external software to exchange data with the system security module for authentication and to grant it access to the required parts of embedded analytics system. This is achieved using a special authentication messages which are filtered out for an exchange of data on each gateway interfaces, while the flow of the regular messages through the module is controlled from each lock interface. The figure 17, secure message gateway connectivity. The message lock provides a simple way to block the transmission of messages, whether for security or for isolating parts of a Tessent embedded analytics subsystem. Figure 18, messages lock connectivity. The Tessent embedded analytics secure message infrastructure provide an entire separate communication system to that of the target SoC, delivering the secure communication independent of the SoC functional buses, ensuring that the behavior of the target system is not impacted. Allow Tessent IP modules to connect and share information across the SoCs, enables sophisticated runtime configurable cross-triggering, provide a transport mechanism for secure control and authentication. Include security locking mechanisms to provide a runtime isolation of the desired portion of an embedded analytics system. The communicators. Bus Communicators AXI. The bus communicators enable software running inside the chip to drive the Tessent embedded analytics system through an AXI interface. Each memory mapped device which enables on-system on-chip software to monitor the behavior of the SoC at any stage of its life cycle, whether that is during the pre-deployment soaking testing or post-deployment security and performance monitoring. The on-chip software could alternatively behave as an agent to remote host, providing access to analytics system over functional interfaces such as Ethernet. The software could be running as a background activity on the SoC's application processors or a smaller processor core dedicated to housekeeping activities. For example, figure 19, bus communicator connectivity. And the Tessent embedded analytics bus communicator enables on-chip resource to communicate with an embedded analytics system. Extends communication method to include functional interfaces such as Ethernet, PCIe, and others. Enables analytics to be performed throughout the SoC's life cycle. USB communicators. The USB 2.0 communicator provides high-speed debug access to the Tessent embedded analytics system for an off-chip debugger or analytics API over USB. There are two variants of the USB communicators. The first variant requires a dedicated USB 5 to be connected to it using either a ULPI or a UTMI interfaces. The second variant includes a compound two-port USB hub, which allows a single USB 5 to be connected and shared between the SoC's functional requirement and the embedded analytics systems. The device implements a Tessent embedded analytics designed cut-down USB Mac core that implement a fixed configuration for pair of the bulk data endpoints and provide dedicated USB connections to the Tessent embedded analytics system. Figure 20, USB 2.0 communicators and connectivity. And the USB communicator is autonomous, requiring no embedded processors or software intervention. The Tessent embedded analytics USB communicators provide a throughput at least 20 times faster than JTAG, is compatible with the widely used USB 2.0 standard, includes hub functionality, allowing a functional USB interface to be shared with the embedded analytics system. Figure 21, USB 2.0 communicators connectivity. The EBC communicators. The EBC communicator provides a high-speed communicator from a Tessent embedded analytics system to an off-chip debugger on an analytics API via USB 3. It provides an AXI interface along with the external buffer controller EBC interfaces for a connection to a functional USB 3.x controller, enabling high-speed bandwidth output from the embedded analytics infrastructure. The EBC communicators interfaces to the external buffer controller EBC port of the Synopsys 3.0 device controller, allowing the data delivery of chip at USB super speed. Figure 22 is ECB communicators. The ECB communicator, EBC, external bus controller. So the Tessent embedded analytics EBC communicators enables USB 3.x super speed, allowing a reuse of the existing on-chip resources and avoiding the costly external probes. It enables closed chassis access after the SoC is integrated into an end product, facilitating the debug and analysis of the SoC throughout the life of the target system. Brings data off chip at speeds in the gigabps range independent of the implemented USB 3.0 standard, fast enough to capture the full instruction trace from the manager, CPU, or capture filtered trace from many cores. Figure 23, ECB communicators connectivity. The Aurora communicators. The Aurora communicators utilize the Xilinx Aurora 8B 10B protocol over a pipe interface to provide a high bandwidth output from a Tessent embedded analytics infrastructure to an external Aurora-based probe, such as route power trace serial probe. The Aurora communicator can also reformat the embedded analytics frames into ARM core site compatible trace port interface unit TPIO frames before being encoded using the Aurora protocol and transported on the SATA link. Figure 24, Aurora communicator connectivity. So, the embedded analytics Aurora communicators enables very high bandwidth output from the embedded analytics subsystems, support up to 8 series range, support either 10, 20, 40, or 8-bit range widths, including optional TPIU frame formatter. JT communicator. The JT communicators provide low bandwidth connectivity to the Tessent embedded analytics infrastructure via the IEEE 1149.1 tested access port. The module implements a simple link layer communications protocol above the IEEE 1149.1 physical signaling layer, which implements a basic flow control mechanism to ensure the lossless communication with the debug host. The 25 is the JTAG communicators connectivity. The Tessent embedded analytic JTAG, the communicator, provides communication with the embedded analytics system over industry standard 1149.1 interface and enables low-cost debug proofs to be used, includes built-in buffering to ensure the optimal use of the bandwidth. So TPIU communicator. The TPIU communicator reformats data captured by the embedded analytics modules into equivalent AMBA core site trace port interface unit TPIU format traces data stream, so that the trace output from the communicators can be accessed by the external trace syncing such as trace port analyzer TPA. Figure 28 is the TPIU communicator connectivity. The Tessent embedded analytics TPIU communicator includes data and control TPIU output interfaces which can be 1, 2, or 4 bits wide. A programmable trace plug with a division ratio of 2 or 4 is generated from a system clock. The TPIU framer supports normal mode of the operation with a single programmable trace ID. TPIU framer encapsulate embedded analytics to frame data, trace source ID, and TPIU frame auxiliary byte in a 16-byte TPIU frames. Optional GPIU interfaces provide a mechanism to provide a configuration signal into external trace control module as needed. The trace communicators. The trace communicators provide a way to drive a Tessent embedded analytics messages into an alternative debug system through external parallel port. It enables embedded analytics system to interface a third-party trace instrument typically offered by processor vendors. The trace communicators receive analytic data contained from an embedded analytics system on its message interface, while it initially buffered before the retransmission of the trace interface. So the trace figure 27 trace communicators here, and the Tessent embedded analytics trace communicator currently supports MB4 ATB protocol, includes parameterizable amount of buffering to smooth out bandwidth peaks, can translate embedded analytics real-time event into a trace triggers on the trace interface, support filtering of unwanted analytics data. The RISC-V debug and trace solution, Tessent UltraSight 5. The Tessent UltraSight 5, part of the Tessent embedded analytic product family, is a comprehensive solution for RISC-V based SoCs. With a combination of embedded IP and software, UltraSight 5 empowers embedded software engineers in developing the high-performance embedded process software. Utilizing the effective, non-transitive techniques such as encoded processor trace based on the efficient trace for RISC-V, each trace standard allowing the high-speed interfaces USB 2.0 and a DMA for fast code upload. The solution minimizes debugging delays and accelerates your SoC products, ensuring they meet their market deadlines. The figure 28 is the Tessent UltraSight 5. The Tessent UltraSight 5 features set of Tessent embedded analytics IPs optimized for RISC-V debug and tracing, processor analytics module, enhanced trace encoder, direct memory access, static instrumentation, virtual console, and communication infrastructure. Long control debug using GDB and OpenOCD, and a flexible Tessent host Suto software platform. UVM-based verification environment. Support USB, JTAG, and AXI for PCIe interfaces. Compatible with common third-party tools including the Visual Studio Code and Router Bajo Trait 32. IP verified by RISC-V core vendors, including the proven down to the 3 nanometer and over 3 kHz. Tessent UltraSight 5 benefits end-to-end debug and trace solution for RISC-V SoCs using GDB. Highly comprehensive processor trace, efficient trace for RISC-V trace standard, the fast system memory access for ELF file upload, and code instrumentation for logging to provide added visibility and performance analysis. The scalable to complete SoC system level debug, optimization, and monitoring solutions. That's UltraSight 5. The system-wide debug and functional monitoring in the solutions. The Tessent UltraSight. Tessent UltraSight, part of the Tessent embedded analytics product family. It's a comprehensive system-wide functional monitoring and debug solution for SoCs with a combination of embedded IP, tools, and software. UltraSight provides actionable insight and produce debugging delays and iterations, thus accelerating your SoC project. This is figure. Tessent UltraSight. So the Tessent UltraSight features set of Tessent embedded analytics IPs optimized for the system-wide debug and trace, bus monitor, state monitor, direct memory access, static instrumentation, virtual console, system memory buffer, processor analytics modules, enhanced trace encoder, and communicator infrastructure. The EA Builder tools to generate a functional monitoring and debug system with the test benches and IP exec for registration description. Host-based Python and C++ APIs to configure and receive system-wide functional monitoring data in real time. USB-based verification environment. Host-based application for processors run control debug using GDB and OpenOCD. Highly compressed processor trace. Support USB, dedicated auto hub, JTAG, CJTAG, and AXI for PCIe access. Compatible with common third-party tools including the VS Code and Router 32. The Tessent UltraSight benefit. End-to-end system-wide functional monitoring system consisting of the hardware and software tooling and verification environment. silicon-proven and pre-verified hardware IPs, cross-triggering and smart filtering capabilities that reduce functional monitoring and data bandwidth, flexible and hosted software to configure and receiving system-wide functional monitor testing in real time, supporting multiple industry and standard interfaces for data transfer off-chip, such as JTAG or USB PCIe, scalable to an in-lab and in-life debug, optimization, and monitoring solutions. The verification IP, the UVM verification IP, the embedded analytics, the universal verification methodology, UVM verification IP, VIP, as a test environment based on the industry standard UVM, containing sequence libraries and integration tests to help development teams carry out a system-level verification of the embedded analytic IP deployed within a SoC. The UVM IP, VIP, facilitated the two core functions of this verification. So, first, verifying the integration of embedded analytics components within each other, verifying the integration of the embedded analytics component into SoCs. The UVM VIP is a set of the software classes and a method that are resided within the test benches and is typically used during a system-level simulation. VIP provide an abstraction level layer which simplifies the task of the design verification. The figure 29 UVM verification IP. So it lets development teams minimize the time they spend on verification. It includes a suite of example tests which check for correct interconnectivity between the embedded analytics IP modules and allow the designers to generate stimulus for UVM system level testing in a structured way without having to get involved in the fine details of embedded analytics methods or frame generation. In addition to the rich library of sequences in a test, a system discovery test is also provided, which includes checks for illegal connectivity. The system discovery process is an iterative method of interrogation in which the topology and capability of every component of the embedded analytics system are extracted and recorded, and may also provide a pass-or-fail result by comparing the discovered system to be expected on previously discovered result. So with the UVM VIP, Tessent is equipped SoC designers with a suite of tools built on a test environment that many already know and use. Designers are free to use UVM sequences, including the UVM VIP, or derived from new sequences from the base sequence classes provided. Okay, digital industry. The GMAN's digital industry software helps helps organizations of all sizes digitally transforming using the software and hardware and services from GMAN's Accelerator Business Platform. The GMAN software and a comprehensive digital twin enables companies to optimize their design, engineering, and manufacturing the process to turn today's ideas into sustainable products of the future. From the chips to entire systems, from product to process, across all industries, GMAN's digital industry software accelerating transformation. Okay, today I read this not paper material, quite long material of the GMAN CDA. Right here. Okay, the Tessent embedded the analytics. So summary guide. This is industry software. Just thank you for your time. See you next time.